Welcome back. We are halfway through the proof of theorem 1 that I stated last time after defining the Kummer extensions, and our goal finally is to prove this main theorem about Kummer extensions, which say essentially that if you start with the right kind of a field, which means it is a field containing a primitive nth root of unity, then a Kummer extension is really nothing but a cyclic extension, and the equivalence is given via two theorems, and the first theorem is to show that a Kummer extension is cyclic. So, we started with the Kummer extension. We argued last time that it is definitely Galois. Now, we are going to show that its Galois group is cyclic. So, I also told you that the roots of, so recall roots of, so the n distinct roots of x power n minus a in k are, so you pick any root that you want first, then you take that root times the primitive roots of unity that exist in k. So, the primitive roots of unity are in f, so they are in k. So, the n roots are given by this, they are all distinct because the polynomial is separable. Okay. Now, we are going to show that the Galois group is cyclic by exhibiting a cyclic group which contains the Galois group as a subgroup. So, for this let us note the following. So, let us take the Galois group k over f and take an element of this. So, then we do know that alpha power n is a. So, this means sigma alpha power n is sigma alpha power n, which is sigma alpha, which of course sigma a, which is a. So, because a is in the base field, so a is fixed. So, this means sigma alpha is a root of x power n minus a. So, hence the conclusion is for all sigma in the Galois group, sigma alpha is some zeta I, right, for some I, because the roots are all in front of you here. The roots of the polynomial are here, sigma alpha is a root of that polynomial. So, sigma alpha is one of them. So, now this allows us to define a map from the Galois group to the cyclic group Z mod nz. Okay. What do we do with this? This is a map phi. So, phi sends sigma to, so the notation here is, so I am going to write this. So, for sigma in G, the Galois group, let suppose we know that sigma alpha is zeta I, zeta power I times alpha. That zeta I will call, that I will depend on sigma, right. So, I will call that the exponent of zeta I sigma. So, then I will simply send it to I sigma mod n. So, I have to be a little careful here because I sigma is an integer. So, it is not in Z mod nz a priori, but I can take its residue class modulo n, then sigma will go to I sigma mod n. So, we will prove some things about this. Phi is well defined first. We will in fact show that it is an injective group homomorphism, and thereby Galois group of k over f is a subgroup of Z mod nz, is isomorphic to a subgroup of Z mod nz, and hence Galois group will be cyclic. So, why is this well defined? The problem might occur if you have zeta I, if you have zeta I alpha is equal to zeta j alpha for different I and j, then I will send via phi, I will send sigma to, if sigma alpha is this, then I will send to either I mod n or j mod n. So, I need to know that I and j are same mod n. So, suppose this happens, then we of course know that because sigma I minus j is equal to 1. So, I can always multiply by sigma j alpha inverse. So, this is sigma I minus j 1. This will guarantee that I minus j is divisible by n. This part here is because because sigma is a zeta is a primitive nth root of unity. It is a primitive nth root of 1. Because of that, if sigma I minus j is 1, I minus j must be divisible by 1, because the order of zeta is 1. So, this implies order of zeta is 1 as an element of k cross. So, its order is 1, right, because it is a finite order element. Zeta power n is 1, and nothing less than n will make zeta 1. That means after n, the next one will make zeta power that equal to 1 is 2n, then 3n, then 4n and so on. So, nothing in between can have that property. So, zeta power anything is 1 implies that power must be divisible by n. So, this is simple group theory here, nothing more than that. That means I is congruent to j modulo n. So, if sigma of alpha is zeta I alpha, which is also zeta power j alpha, then I is congruent to j mod n. So, phi of sigma is well defined. See, a priori you might write different integers, but when you look at the residues modulo n, you get the same answer. If you take Galois K over F to Z, you will not get the same well defined map, because maybe n is 5 and then zeta power 7 equals zeta square alpha, right. So, where will you send sigma to? So, if this is sigma alpha, sigma will go to either 7 or 2. So, if the target is the integers, this is not a well defined map. However, if the target is z mod phi z, 7 bar equals 2 bar. So, there is no problem. So, I am just really explaining too much perhaps, but this is a well defined map, and that requires the fact that zeta is a primitive nth root of unity. Second statement is phi is a group homomorphism. Why is this? So, phi is a group homomorphism. So, of course, this is a group, this is a group. So, this is a group homomorphism, and this is rather easy, because what is, so suppose sigma 1 of alpha is zeta I sigma 1 alpha, and let us say sigma 2 alpha is zeta I sigma 2 alpha. Okay. So, then what is sigma 1 sigma 2 of alpha? Sigma 1 sigma 2 of alpha, which by composition, right. So, this is zeta I sigma 2 alpha, then you apply sigma to this, zeta I sigma 2 is a constant, because that is in the base field. So, that comes out, and then sigma 1 of alpha is I sigma 1 alpha. So, right. So, this is sigma 1 alpha. So, zeta power I sigma 2 comes out, and then you get this, but this is nothing but zeta I sigma 1 plus I sigma 2 alpha. Now, if you go back to the definition of phi will send anything to, you simply apply sigma to alpha and then see what is the exponent of zeta. So, to find the image of sigma 1 sigma 2 under phi, you look at the image of alpha under sigma 1 sigma 2, and that is, so basically this entire calculation shows that I sub sigma 1 sigma 2 is I sigma 1 plus I sigma 2. Okay. So, maybe this is a bit confusing if you are seeing this for the first time, and I am going maybe a bit fast, but just pause the video. There is really nothing more than notation here. This is not Galois theory, this is just keeping track of the notation. So, phi sigma 1 sigma 2 is, you look at the image of sigma 1 sigma 2 and image of alpha under sigma 1 sigma 2, and look at the exponent of, because that is a root of x power n minus a, it must be a power of zeta times alpha, and that power is this. So, this is I sigma 1 plus I sigma 2, and by the well definedness I can take anything here, I mean any integer that has this property. So, this of course is, this is modulo n, of course, because that is the group. So, this is a group homomorphism. The operation of the left hand side group is composition, the operation of the right hand side group is addition. So, phi of sigma 1 composed sigma 2 is phi of sigma 1 plus phi of sigma 2. So, this is a group homomorphism. Finally, phi is injective. Why is this? So, this is also easy. Suppose something is in the kernel, that means its image is 0, which is the identity element of this. But this means I sigma is 0. This means sigma alpha is the 0th power of zeta times alpha, right? But that means sigma alpha is equal to alpha. Once sigma alpha is alpha, now recall that k is f alpha, because once you adjoin alpha, all the other roots are also already contained. So, the splitting field is generated by alpha. So, if sigma fixes alpha, so sigma of if you want beta is equal to beta for all beta in k, because of course sigma fixes capital F, it fixes alpha, so it must fix every polynomial in alpha. That means sigma is identity element, right? So, it is injective. So, that means Galois group is isomorphic to a subgroup of Z mod nz. Now, since Z mod nz is cyclic, so is the Galois group. So, this proves the first statement of the theorem 1. K over F is a cyclic extension. Now, we will get to the second statement, but we can conclude now. So, K over F is cyclic. So, K over F is cyclic. So, now next we have to prove, I will write it down, K colon F is, which is the Galois group, because it is a Galois extension, the degree of the extension is same as the order of the Galois group, if and only if x power n minus a is irreducible. So, this is what we want to show. So, now let us show this. So, K colon F equals to n implies because K is F alpha, right. So, K colon F is n means F alpha colon F is n. This means degree of G is n, where G is the irreducible polynomial of alpha over F, right. If you have a primitive extension like this generated by a single element, the degree of that extension is simply the degree of the irreducible polynomial of that primitive element. So, if G is the irreducible polynomial, degree of G must be n. On the other hand, note that F alpha is 0, where F is our polynomial whose splitting field we started with. So, F is x power n minus a, then F alpha is 0. So, G divides F. G divides F and degree G equals degree F equals n. F is already a degree n polynomial. That means F is G is irreducible, in other words. It is irreducible over F. So, if K colon F is equal to n, then F must be irreducible. So, F is this. Because the irreducible polynomial of alpha, whatever that is, must have degree n. F is a polynomial which has alpha as a root. So, F better be the irreducible polynomial, and of course, that means F is irreducible. On the other hand, this is one direction, right. If the Galois group, so I did not write this completely, I mean this. If the degree of the extension or the order of the Galois group is n, that is irreducible. Now, suppose this is irreducible. This of course means that degree of so this implies, this is what I am assuming, but note that the order of the Galois group is less than or equal to n, because this is because the Galois group is contained in the group Z mod nz, and this has order n, right. So, if you have this as order n as a subgroup, this will have order at most n. Now, this implies, so the degree of the extension, which of course is the Galois group order, because the extension is Galois, is less than or equal to n. On the other hand, k colon f is f alpha colon f is is what am I assuming? It is irreducible. So, this is equal to it is actually equal to n. So, I did not need to do all this, because what is the irreducible polynomial? X power n minus a is irreducible by hypothesis, and alpha is a root. So, f is irreducible and alpha is a root of f, right, and hence, so this follows, right. So, this entire thing here implies this. So, k colon f is equal to n, which is what we wanted to prove. So, that I did not really need this. I did not need this. Those are of course correct statements, but I do not need any of those. Directly we can argue this, because x power n minus a is irreducible. So, that is a polynomial whose root is alpha. So, the irreducible polynomial must be that, and hence the degree is n. So, this completes the proof of, this proves theorem 1, and hence it proves the one direction of theorem, main theorem. So, this is the main theorem. Remember, 1 implies 2 is theorem 1. Okay. So, this completes the proof of the first part, which says that if you have a Kummer extension, then it is a cyclic extension. So, basically think of this, there is a lot of stuff here, but think of theorem 1 as Kummer implies cyclic, and think of theorem 2 as cyclic implies Kummer. This is just a short way to remember, but remember also that it is not I mean there is a lot of additional hypothesis here, that f is a field containing a primitive nth root and so on. So, if you remember all that, a convenient way of proving remembering theorem 1 is Kummer implies cyclic, and convenient way of remembering theorem 2 is cyclic implies Kummer. So, we now proved Kummer implies cyclic, and theorem is that Kummer if and only if cyclic. So, we are done with first theorem. Theorem 1 has a little more data than just Kummer implies cyclic, but that is a crucial thing for us. So, I wanted to highlight that. Now, let us go ahead and start the proof of theorem 2. Okay. So, theorem 2 I will write down just for so that I do not need to go back to that slide. F and n as above, that means n is a positive integer, f is a field with the characteristic assumption star, and that f contains primitive nth root of unity. K over f is a cyclic extension. So, that is the part of hypothesis. K over f is a cyclic extension. Then the statement is K is the splitting field of any. So, then K is the splitting field of an irreducible polynomial x power n minus a over f. So, of course, a is in f. So, this is the statement. So, this of course, as I said, is really saying that cyclic implies Kummer. So, these things will in fact be useful for us later. These are not just of intrinsic interest, which they are, but they will be useful to us later also. So, let me start the proof. I may not have time to finish it in this class, but I will continue prove for some time and then we will stop. So, let us see. So okay, so let me start the proof and then see how much we can do. So let G be the Galois group. So note that K over F is Galois is by assumption and G is cyclic. So that is the assumption that it is a cyclic extension. So now our goal is to produce a small a in capital F whose nth root will generate K. So let us also fix a primitive nth root of unity in F. Because F contains an nth root of unity, I will just take one of them. Okay. So let me maybe, I am not sure I can finish the proof in 10 minutes. So I am going to stop this class here and then we will use the next class to prove this theorem. Thank you.